So lab 5, right, so lab 5 was, it's on Moodle, and it's, here. Right, so this is the case that I talked about it briefly, I think, before last Tuesday, I think. And then I was talking about how you can specify different types of prior for a simple linear regression. So the lab 5 is here, like the details are here. I gave you some sample code. But before we start doing it for like 30 minutes or so, I want to maybe just quickly go over what was the conditional mean prior that we talked about briefly. So yeah, so this was the right. So conditional means prior is trying to not putting prior directly on betas, because betas are hard to interpret it if you don't standardize the data. So we're trying to walk around and to figure out a way, what if we can think about some other ways to convey the prior if you do have a prior belief. So what we're going to do is you're going to work on the original scale of the data, and then we're going to try to state prior beliefs about the expected response value, which is those mu, conditional specific values of x. Okay, so instead of working with beta 0 and beta 1, we're going to work with mu and x, like two sets of mu and x, because from there we can solve the equation for beta 0 and beta 1. Okay, so that's the general approach. And what you do is we're going to assume independence again with about all of the coefficients here. And then we're still working with this equation 33, which is the linear relationship between the mean and the predictor. Okay, still beta 0 plus beta 1 times xi. So in order to avoid dealing with beta 0 and beta 1, we're going to try to formulate prior opinion about the mean values. In our case, is the log, the expectation of the log expenditure. Okay, that's the outcome. And then x is the log of the income. So for example, if you think that if you have log income to be 10, which is x1, say x1 equals to 10 here, I think the mean, which is mu1, if we use the same notation, I think is going to follow normal A2. If that's what you believe in, then you can actually assign prior to mu1 directly. Okay? And then, for example, I come up with another value for x, which is I use x2. If I think the log income is at 15, and I think the mean of that particular mu, which is mu2, going to be normal 11.2, then I can assign this directly to mu2. So the reason why we're doing two sets, you can see here, mu1 x1 and mu2 x2, we're doing two sets because we have two unknowns that we're trying to solve. So the two parameters that we try to solve is beta 0 and beta 1. There are two of them because it's simple linear regression. Okay? So that means if you're trying to use this conditional means prior approach, you have to set two x values and then give the corresponding, say, prior distribution. In this case, the two normals to the two means. Then you can solve beta 0 and beta 1. Okay? So this is indirectly giving priors to beta 0 and beta 1. You specify your prior on the expected outcome, and then given a particular x value. So last time I showed you this already, so I think it's probably not too surprising. So equation 38 and equation 39 is, well, if I have two unknowns, beta 0 and beta 1, and I have two knowns or two equations here, which is like mu1 equals to beta 0 plus beta 1 times x1, and then mu2 equals to beta 0 plus beta 2, beta 1 times x2, then I can just solve them. Okay, so this is pretty straightforward algebra. And beta 1 is the ratio of the difference in the mean and the difference in the predictor values. And beta 0, you can use two different ways to express it, but whichever is going to give you the same result. Okay, so this is because we're dealing with simple linear regression, and we are having one continuous predictor. So our expression, the linear relationship is beta 0 plus beta 1 times x equals to mu. And because of that, we can specify conditional means prior in this way. Okay? The thing is, you might be wondering, okay, what if I have two predictors? Both of them are continuous. So I'm going to have what? Mu equals to beta 0 plus beta 1 times x1 plus beta 2 x2, right? That will be the general expression. So now you have three unknowns, beta 0, beta 1, and beta 2. So if you want to use conditional means prior to do it, you will have to have three sets of means, right? And in fact, the derivation, I would say the expression for solving the beta 0, beta 1, and beta 2 is crazy. So usually people don't do that. But what I mean, so let me just write it here. If you have mu equals to beta 0 plus beta 1 x1 plus beta 2. So this is what we're going to cover today as well, multiple linear regression, that you have more than one predictor. And then the conditional mean priors will be much harder to specify. So first of all, you have three unknowns. So you're going to have mu, like three set of mu and x. You need three sets of them. But even so, just think about it. You have three unknowns and then three equations. Solving beta 0, beta 1, beta 2, the form is going to be much more complicated than what we have in 38 and 39. So that's why it's not typically done. Okay? But you can do it if you want. Okay? But in our class, we're just going to cover the simple linear regression case with the conditional means prior. And the reason is, well, giving prior to beta 0, beta 1 might not be intuitive. But you might have better understanding or better guess of, say, if I know consumer unit log income is a fixed value, say like 10, that's what we saw earlier, you might have a good guess of what the mean should follow, like the distribution that the mean should follow. So you can go from there. Okay? And then in terms of mu2, then if you have your log income to be 15, and I think, okay, the log expenditure should be centered around 11, and then with standard deviation 2, then that's what it is. Yeah.
Yeah. So do we have like a principal way of like assigning these conditional mean hyperparameters? Like that's the only part of school.
Yeah. So well, that's I mean the question is related to if we ever have a principal way to give prior belief in the way that we want. Right. So in this case, again, I think it's based on the context. Okay. Yeah. And I have to say, I mean, the particular consumer expenditure survey sample that I'm working here is just, it's probably not the best one to deal with because we're working with log scale. Right. Like I came up with those numbers just to like transform the log and then think about on the original scale. And then came up with sort of, I still don't know if it's true. But again, prior, especially about the standard deviation, I think putting it larger wouldn't hurt. Yeah, just because, well, that's controlling how strong your belief is, right? So I think it's most important about the mean.
Right, so it doesn't matter like how vague the prior ends up being.
Oh, I don't think so. Because at the end, so if you give a vague prior here, then yeah, then the posterior is going to be driven mostly by the data, which is not a bad thing anyway. And that's the first, I think the first set of prior that we introduced is the weakly informative prior, right? We're working on the original scale as well. And then we give what? Beta 0, center as 0, and then super large standard deviation. And then beta 1 as well. Yeah, so that's like super weakly informative. We're just gonna let the data decide. Okay, so here, similarly, if I just have a good sense about what the mean should be, then I can put that into like my normal mean here in like my M1 and M2, and then S1 and S2 can be, I think, flexible. All right, so now you might be wondering, okay, so how can JAX do this for us? So obviously, we're not going to give prior distribution for beta 0 and beta 1 anymore. We're going to give prior distribution for mu1 and mu2. Okay? And to get to mu1 and mu2, we need x1 and x2. So those are the values that you're going to use later. So the script that I shared, which is in the lab 5 as well. So lab 5 is working on how you can finish the rest of the analysis given this particular conditional means prior. So let me just walk through this really quick. So the first part is still the same. The sampling part, we still have beta 0 plus beta 1 and then times the predictor, right? And then that's the inverse gamma. So that's all fine. So what's changed here is the way that we specify the prior. Okay? And mostly just this 4 lines. So previously, we gave beta 1 to be like d norm something something, right? Beta 2 to be d norm something something. But now we're specifying normal prior for mu1 and mu2, and then use the 2 equations that I showed you earlier for beta 0 and beta 1 to get the actual values for beta 1 and beta 0. Okay, so this last 2 lines here is the one that I'm giving prior for mu1 and mu2. So as we discussed earlier, it's going to be one is at mean 8, the other one is at mean 11, right? And for the G, again, this is precision, so you have to like compute the right number, but I was giving standard deviation 2 for both cases, okay? And then the important steps here, so first of all, keep in mind, only when you're giving a prior, you're using this tilde, okay? But then this relationships, they're deterministic, okay? They are equations like you solved it before. So that's why I use this assignment for beta 0 and beta 1, okay? And then the 2 assignments is exactly the 2 equations that I showed you earlier. Okay? So in the end, in your data section, when you try to fit data into JEX, you will have to give values of, I mean, obviously obviously M1, G1, M2, G2, and also you have to give X1 and X2. So those are the new things, okay? And for inverse gamma, well, inverse sigma, sorry, we're still going to use gamma, and you can just use gamma 1, 1 for that case. Okay, so A and B, you still need them. Yes?
Do you still need Y and X?
Oh, yeah, you always
All
need
those
that.
data.
Right, yeah.
Right.
So Y going to be the data, I mean, the outcome, which is the log, the log expenditure, and then X is the log income. Yeah, so that's all I want to say about lab 5, and I have to, let's just spend some time, like 20 minutes-ish, walk around to answer questions, and if anything like common come up, I will just address it in the recording, and after that, I will just cover the last few slides about multiple linear regression, and then we're going to end this today.
M1.
All right, just one general comment here that I noticed many of you run into the issue. So it's 2 things. First of all, I noticed some of you are just copying like this, the model code, then into R. It works fine, except there's this extra 1 here, that's the page number. And then it just doesn't work in JAX, so it's going to give you error messages. So I recommend you either just type yourself, or go back to the slides, I think. I mean, mostly just like replace those 2 lines, because that's where it happened with that page number. But the rest should be fine. There's that. And then another thing is some of you are asking, I mean, question 1 is, well, you have to. So I was giving you the hint that you should give those values in the d_data part. So I didn't include any sample code in the document here, but I mean, that's what we usually do with the d_data. You're going to give y, give x, give n, et cetera, et cetera. So that's where your M1, G1, M2, G2, and then X1 and X2 should go. Okay, so in terms of what they are, you should come back to equation 7 and 8 here. So I'll just do one demo. So we know that X1 should be 10. So that should go into the data section. And also, so that's this 10 here. And also, we are giving mu1 to be a normal prior with mean 8. So your M1 should be 8. Okay? That's this M1 here. And then your M2 should be 11. So that's your M2 here. And then one last thing is here, for the d-norm in JAX, it only takes precision. So you have to, so this is standard deviation. So with standard deviation 2, your precision is 0.25. So you have to give G1 and G2 0.25 in the data section. Then your code should go. Okay? And then I'll leave it for you to do the rest, of course, interpretation of beta 0 and beta 1. And then, of course, the last one is, the second question is make sure that you perform against CMC diagnostics. And last question, question 4, is do some prediction. And then the hints are in the slides. Okay? So let's spend maybe 5 more minutes on this, and then you can finish it after class and then submit it later. One more quick comment. Some of you are running into issues, like even though the code looks perfect, it just doesn't run. I noticed some of you missed this standardization step. So as you see that we're working with the standardized log total expenditure and standardized log total. Should we use the standardized? I thought no. No, right?
No.
Okay, so that's why you guys cannot follow the code one by one. You have to think. We're not using the standardized. Sorry. So what you should do is you change your X and Y input. Sorry. So click off. You don't need it. So obviously here, if you just copy and paste whatever it's there. So this was the weekly informative prior that we standardized the data. Okay. Now we don't. With the conditional means prior, we're not standardizing. We're just using the original log scale.
Yeah.
So your X and Y shouldn't be, say your Y should be CE data $ log _ total EXP. That's it. Okay. And then the same goes for X. So yeah, good call. So that's the issue. Some of you might notice that in your work environment, there's no X and Y because it's never get past two checks, and that was the reason. Okay, so get rid of the STD, and you should be, yeah,